If we want to measure the rate of change of some voltage signal that might represent a temperature or a position or something like that, then to measure that rate of change, basically we have to measure the actual voltage at two different points in time and then look at how much it changed over that length of time. So we take our derivative and we approximate it with a finite difference, the change in voltage divided by some short change in time, delta t. And that'll be just V2 minus V1 over T2 minus T1. Problem is, that introduces some uncertainty because we're not sure about our measurements of either of those voltages, and we're not sure exactly what time we took those measurements. So how good is the estimator? If we're making an estimation of our slope on average over the region between those 2 points, then a line, a straight linear line passing through those 2 points, is a pretty good estimate of that line there. It's not such a good representation of this one or that one, but it's a pretty good estimate of the average between them. So as long as we keep this time delta t fairly short, then our estimator, our finite difference estimator, will be pretty good. Now suppose we set out to measure it. The next question is, how good is our measurement? Well, to do that we need to assess the uncertainty in the result of our measurement. So the uncertainty in our result is going to depend on the uncertainty in V2 times the effect of V2 on the overall result. So for that we need to know what the change in R will be for a change in V2. Likewise, uncertainty in V1, dr dV1. Uncertainty in T2, dr dt2, and uncertainty in T1, dr dt1. Now again, because we're combining multiple probability distributions, we take the square of each of these contributions, sum them up, and then we take the square root. So we're only going to be interested in the magnitudes of each of these contributions because it's going to square. So let's look at these derivatives. If we take the derivative with respect to V2, it'll just be 1 over T2 minus T1. If we take it with respect to V1, it'll be negative 1 over T2 minus T1. Or, and we only need to know what the absolute magnitude is, dr dV in both cases is 1 over the magnitude of T2 minus T1. Similarly, the magnitude of the rate of change of R with changes in T, either for T2 or T1, it's going to have V2 minus V1 on top divided by T2 minus T1 squared. So if we've got this uncertainty in our result and we're making the voltage measurement with the same voltage device and the time measurement with the same time base, then the uncertainty in the voltage will be the same whether we're looking at V1 or V2, and the uncertainty in time will be the same whether we're looking at the uncertainty in time T1 or T2. Plugging that in, we get UR equal to 2 times UV over T2 minus T1 squared plus 2 times UT times V2 minus V1 over T2 minus T1 squared, all of that squared, and then the whole collection square root. So let's look at this relationship. It says that there's a factor of 2 because we've got 2 times that we're measuring and 2 voltages that we're measuring. There's an uncertainty associated with the fact that we don't know the voltage as well as we might like, and with the fact that we don't know the time as well as we might like. And those are modified by the actual changes that we measured. How big were the differences between the voltages and the time? So this uncertainty gets large if delta t is small. Gets large if delta t is small, or if delta v is large. Or, of course, if either of the uncertainties in either the voltage or the time scale are large. Now suppose we had a slope of about 1 like this. So if dV dt was equal to 1 volt per second, then if we took our delta t for 1 second, our delta v would be 1 volt. If the uncertainty in the time base was 1 millisecond, and the uncertainty in the voltage was 1 millivolt, then the combined uncertainty in the result, measured also in volts per second, because that's the rate of change that we're looking for the uncertainty in, punching the numbers through, that winds up being 0.002. 1 part in 1,000 error in each of these turns out, once we do the math, to give 2 parts in 1,000 error in this slope result. Suppose we did it a little faster. Let's do 100 samples a second, so 10 milliseconds delta t. That would translate to 10 millivolts delta v. If we stuck with the same 1 millisecond and 1 millivolt accuracy, we'd have an uncertainty of 0.200. So that's 20%. We could make this better by improving the time base. Let's stick with our 10 milliseconds and 10 millivolts and make this 10 microseconds of uncertainty in the time. So almost exact. And stick with our 1 millivolt here. That gets us 0.141. Let's go to 50 milliseconds. So instead of 100 samples per second, we're going to look at it just 20 times a second. That should see a change of 50 millivolts. If we had our same 10 microseconds time base and our reasonable expectation of about 5 millivolts accuracy on our voltage measurement with our Arduino, then we'd still get about 0.141. So this derivative is not going to be nearly as accurate as what we were expecting based on our voltage measurement. And that's because we're taking the difference between 2 voltages over a short time. If we tried to go back to our 10 milliseconds, 10 millivolts, with our 10 microsecond time base and our 5 millivolt voltage accuracy, we'd have an uncertainty of 0.707. 70% of the actual measurement. So very poor accuracy if we take that very high speed, unless we can improve on the accuracy of our voltage measurement.